This presentation focuses on sacrificial shield model, a tactical re-evaluation of how unburned anthracite interact with the furnace skeleton in the lower furnace. By the end of this 15-minute briefing, we will have a clear directive on why a 6% AUPC ratio is the optimal threshold for preventing catastrophic structural degradation. Coming to the topic, actual topic, the AUPC passivation. Let's be honest, usually when we talk about unburned coal, we are talking about a headache for permeability. But what if it's, well, actually, what if it's the solution to our coke strength problem? So look at the title screen. Our focus is specifically on 1100 degree centigrade isotherm co-gasification. The 6% protection limit, that is not just a random number, it's our metallurgical sweet spot. We are not just looking for high PCI, we are looking for metallurgical optimization. The core idea here is that by optimizing uh, how anthracite co-gasifies with our coke, we can maintain a structural integrity in the most hostile zone of the furnace, that is the lower zone of the furnace. So if we hit that 6% threshold, we are not just burning fuel, we are building a defenses. So, but to understand the defense, we have to look at why we even have this waste material in the first place, the harsh reality of the raceway. Now coming to the incomplete combustion. Here, think about our modern furnaces. 100% combustion as well. It's basically a myth. Look at that injection point. You have got a massive volume of coal hitting a high velocity airstream in an extremely limited space. Under these circumstances or in this condition, limited space and incredibly short residence time, complete gasification is physically impossible. That is, we are talking in context of 12 to 15 millisecond. So anthracite unburned pulverized coal or AUPC inevitably escape the raceway and start accumulating on the coke skeleton. Historically, we viewed these purely as a liability that choke your gas and liquid permeability. And look, it can do that, but we need to look past the liability to see the tactical advantages. This brings us to a complete paradigm shift in how we manage that accumulation, what we call the passivation model. So now coming to the AUPC as a sacrificial shield philosophy. So let us refer to the legacy view. Say AUPC is just a byproduct that ruin your stability. But I want you to look at the right side of your screen. You see that light blue glowing layer wrapping around the coke. That is our sacrificial barrier. When we maintain that optimized 6% threshold, the AUPC act as a sacrificial shield. It preferentially reacts with CO2 as that the coke doesn't have to. We are literally shifting the inner pore gasification, which destroy coke from the inside out to the outside surface of the AUPC. This delays degradation and quite frankly, is the only reason we see such massive boost in high temperature tensile strength. But why does AUPC react so much faster than the coke? It's all about the physical engine of the particle themselves. So coming to the physical engine reactivity. You might think anthracite is just anthracite, but the furnace, well, it changes the DNA of the coal. Look at the SEM image on the left, raw anthracite. It's smooth, dense, and has no obvious pore. Now look at the AUPC post combustion. It looks like a porous sponge. The thermal shock of the tuya transformed that smooth anthracite into highly porous structure. This massive increase in surface area is our secret weapon. It guarantees that the AUPC will preferentially react with CO2 long before the CO2 can find a path into the coke's internal pores. It's about being a better target for the gas attack. Now let's look at the actual math of that preferential attack during gasification. So in understanding the co-gasification dynamics, that is at 1100 degree centigrade isotherm. So because feeling like it's working is not enough, we need to see the mass saved. Look at the chart. The gray line is unshielded coke. The blue line is our coke plus 6% AUPC. In phase 1, the first 500 seconds, the AUPC wrapped coke shows a higher initial fractional weight change. And that's a good thing. The AUPC is acting as a decoy, absorbing that initial aggressive CO2 spike. By phase 2, the carbon loss stabilizes. By the end of the run, we have restricted carbon loss to 12%, saving exactly 2.7% of the critical coke mass compared to the naked operation. But it isn't just a surface area game. There is a chemical glaze forming that seal the deal. So now coming to the mineralogical catalyst agenda, that is shifting as chemistry. Now this is where the mineralogy takes over. We are moving from dry clumping to fluid sealing. On the left, naked coke forms mullite, its high melting point, high viscosity, and look, it's useless. On the right, our shielded coke is forming calcium iron oxide. We are seeing a fundamental shift in high temperature as chemistry. The AUPC as react with the coke as to dramatically lower the melting point and viscosity of the slag also. So we are essentially converting a dry abrasive ash into fluid protective glaze that can actually move and cover the surface. And that glaze led us to most critical physical process on the coke surface, that is ash wetting. Now coming to the our this slide on the passivation mechanism, how the ash wetting occur. So imagine that low viscosity slag just well spreading like water across the carbon matrix. You can see it, the fluid slag flows deep into the macro and micropores. This is a three-step process: fluidity, penetration, and finally passivation. So by flowing into those pores, the slag physically block internal gasification. We are forcing all the CO2 degradation to stay on the outer surface, which preserve the structural skeleton, our core of the coke. So the big question is, does this shield actually keep the coke from shattering? So now coming to the our this slide, which is about a tensile strength retention. So this is the payday slide. This is why we care about unburned coal ratio. Look at the center. Reacted coke without a shield dropped to terrifying 5.6 MPa. But with that 6% AUPC shield, we are at 8.8 MPa. That is a plus 3.2 MPa recovery. So by restricting gasification to the surface, we are retaining nearly 60% of the original 14.8 MPa coke strength. Without that shield, you are looking at devastating 62% loss in integrity. That is the difference between a stable hearth and a catastrophic structural failure. But you cannot just keep piling on coal. There is a hard physical limit, and this slide talks about those limits. The 6% protection limit. Is more always better? Definitely not. We have to talk about the risk index. Look at this dual axis dashboard. The blue curve is our tensile strength. The orange dashed line is our furnace permeability risk. At 4% AUPC, you are under shielded. You only get about 1.85 MPa of recovery. But once you go past 6%, roughly 130 kg per ton hot metal of PCI, you hit diminishing return. So tensile strength stalls out at 8.7 MPa. But look at that orange line. Your permeability risk skyrocket because excess coal start choking the gas and liquid flow. 6% is our optimal optimization zone. To keep this straight, let's look at the step-by-step sequence from the raceway to the hearth. So, coming to the passivation sequence. So, let's follow a single coconut as it exits the raceway. Step 1, preferential attack. Step 2 is the chemical shift, whereas step 3 is the viscosity drop, and step 4 is the ash wetting. Step 5 is the integrity maintained. So this is a chronological journey. The AUPC absorbs the first CO2 hit, the mineral shift from light, the slag melt and wet the pores, and finally the core tensile strength is retained for lower furnace. This sequence ensures that the coke stays strong exactly where the mechanical pressure is at its peak. So what does this mean for your next shift? Here is the playbook. So what this operational playbook says, the UPC optimization. So here is your no boat takeaway. So stop viewing AUPC as just waste material. With open hands, uh, with open minds, our target should be at least 6% AUPC ratio, which is equivalent to roughly 130 kg per ton of hot metal. So our goal is a tensile benefit of 8.8 MPa. So do not view a zero AUPC state as the ideal. We need to target that 130 kg per ton hot metal PCI rate to maintain that protective pacification layer without triggering those permeability alarm in the upper shaft. So it's a balancing act, but now you have the math to win it.